My name is Pranav and this is my AE1601 glider project report about my glider, which I named the Bounty. The requirements for this glider were to fit within a 16-inch by 16-inch size limit and fly a distance of at least 20 feet without breaking apart during the duration of the flight. For this project, my glider went through 2 iterations, the details of which I will be explaining throughout this report. Though balsa wood had already been pre-decided for the material, I thought it was ideal due to its high strength-to-weight ratio. Though fragile, it was strong enough for the purposes of the project while also being very lightweight. For my original sketch design, I opted for a fuselage of 10 inches, which is not too big or small, and I made my wings with a tapered design being 6 inches in length, each positioned at 2 inches from the tip of the fuselage, which I determined I should do using a drawing with reasonable proportions and relative values. By using some basic mathematical calculations and research, I determined an aspect ratio of around 7.5 was good, since a guide for a similar glider competition informed me so. I altered the wing dimensions such that my aspect ratio was almost exactly 7.5. I did this because most gliders have massive wings with a high length-to-width ratio, according to a research paper by NASA. I also decided on a dihedral wing design over a flat or anhedral design for lateral stability to avoid possible shakiness during the flight. I also added small wing tips for less drag near the top of the wings for a longer, smoother flight, since less drag means less opposing forces on the glider, meaning it would fly farther and longer. I also went for a fuselage-mounted tail configuration for simplicity reasons over other designs I could have used. I then implemented the design that I created in a prototype that used cardboard and tape instead of the wood and superglue to avoid wasting my limited materials, and though the 20 feet was easily obtained, the glide was not smooth, and it faced a problem where the glider veered to the right. It felt more like a throw than a glide, so it was back to the drawing board. I took my original glider design and modified it to make it more effective. I made my wings 2 inches longer for an overall wingspan of 16.5 inches, while keeping the root and tip cords the same and also keeping the position the same. But the biggest change that came to my redesign was the tail fin configuration, which I made significantly bigger, which I hoped would make a change because of the increased surface area contact with the air, making it 6 inches wide and having cords of both 2 inches and 1.25 inches respectively. I also made my vertical stabilizer bigger, a trapezoid with bases 2 inches and 1 inch and a height of 2 inches. These are my calculations for the lift and drag coefficients. I started by getting the weight of my glider, which I did by getting the mass of the glider, which was 29 grams or 0.029 kilograms, and multiplying it by acceleration due to gravity 9.81 to get 0.28449 newtons. I then got the wing planform area, which is the area of one wing on one side, which I took to be a trapezoid with bases 2.25 and 1.25 and a height of 8 inches to get 14 inches squared or 0.00903 meters squared. I then got B, which was my wingspan, which was 16.5 inches or 0.4191 meters. I then used multiple videos of my glider flying to get the distances and the time based on the timestamp in the video, and took the average of those to get the average velocity, which was 22.7122 feet per second or 6.92 meters per second. I then used the lift coefficient and the drag coefficient formulas to get the values of each. Using the lift coefficient formula 2W over rho infinity v squared s, I plugged in my values to get a lift coefficient of approximately 1.0519. I got my rho value of 1.255 kilograms per meter cubed from the internet. To calculate the induced drag, we use the formula CDI equals CL squared, where CL is what we calculated before, divided by pi EAR, where AR is the aspect ratio of the wings. We plug in the values to get a CDI value of 0.0403. We can then make the assumption that the induced drag coefficient is equal to the zero lift drag coefficient, and the final drag coefficient is equal to the sum of both. And so you'd get 0.0403 times 2, which is 0.0806 for the drag coefficient. Then came the task of actually building the glider. I designed all of my parts using a program called SolidWorks, and I did this in order to get each of my parts swiftly laser cut at the Aero Maker space without having to manually cut them by hand, and then I superglued them together based on my design. Then it was time to test the glider. With this updated design and also higher build quality, the glide seemed a lot smoother, but figuring out the optimal mass of Play-Doh took a lot of testing and fine-tuning, as multiple tests showed the glider stalling because there was not enough mass, or it nosedived because it had too much mass. After all the fine-tuning and getting the optimal mass, I determined that the center of mass was at 4 inches from the tip of the Play-Doh, which is behind the quarter chord line of the wing. I also added some tape on the left side to add mass to the left side in order to hopefully account for it veering to the right, which was likely due to a slight misalignment of the vertical stabilizer when supergluing it on. By launch day, I hoped I was set. Unfortunately, I was not completely set, and for my official glider fly-off flight, as you can see in the video above, the glider did fly to the right. Even though I did get beyond 20 feet, it wasn't a perfectly straight flight. Here's a video that shows the best flight that I got that day.
Yeah, that was the best one. What the f?
Oh, that was so nice.
I'm saying.
Get in the next round.
10, 20.
Just run it back.
His S is not beating too much.
It's okay, let's do it again.
80?
After some practice and getting the angle of attack just right, I was able to make my glider fly a distance of 80 feet in a straight line, showing how the new iteration overcame the limitations of the previous. Overall, I feel like the glider project was a good test of my engineering and design capabilities, and an excellent yet simple demonstration of the engineering process. I hope to one day rebuild my glider with more durable materials and aim for at least 100 feet in distance. I would like to give a thanks to both NASA and the Milwaukee School of Engineering for their information on gliders, and thank you for your time.